Good afternoon, everyone. Thank you for providing me the opportunity to discuss my work here. It has been done with Professor Sriram Ramaswamy and Professor Shubhrata Mukherjee at ISC. Let's start. The talk is perturbation spreading in a non-reciprocal classical isotropic magnet. Yes. So classical Heisenberg spins in a large temperature limit and at long times, they show thermalization and spin diffusion. So the earlier work was done for precessional Hamiltonian dynamics. In this work, we introduce non-reciprocal kind of coupling that was first studied by Joyjit Das et al. And what effect it brings into the dynamics. And then it is studied in the context of a decorrelator, which was studied by members of the ICTS group for the Hamiltonian dynamics case. And eventually, I will talk about the non-equilibriumness of the equation through a power dissipation calculation. Okay, so spins of unit length, the system is a spins of unit length which precess in a local field, and this is the most generalized way they interact. There is a precession with the adjacent terms, and if it is a purely reciprocal coupling, then Jx x plus 1 is equal to Jx plus 1 x. However, that needn't be the case always. We consider the most extreme limit in our work, and we take the left-right coupling to be opposite of each other, non-reciprocal, basically. And that gives us this equation, S dot is equal to mu Sx cross Sx plus 1 minus Sx minus 1. And that is the equation primarily under focus. And then we compare our results with the classical Hamiltonian dynamics case. And mu and lambda are the precession coefficients for the two respective equations. Okay, our system is chaotic at infinite temperature, and the chaos can be quantified using divergence, measuring the divergence of the dynamical trajectories. So a classical out-of-time ordered correlator is one quantity that is used for this purpose. So it's defined as shown here. And the decorrelator that has been defined again through the Avijit Das et al. Paper is nothing but a time evolution of the spread of a spin copy. The divergence of a spin copy from after perturbation, and that is averaged over an infinite temperature thermal distribution. So this is the equation for the decorrelator. And just to be more specific about what the perturbation is, that we take a copy A, and at just one specific site of that spin configuration, this perturbation of strength epsilon is added. And the equation basically that describes that slight deviation is basically a global spin z axis is taken for that, and it's taken a cross product with that spin at site 0. And after normalization, we get the delta S naught, the perturbation at that specific site. And that decorrelator, after all this equation, can be related to the OTOC through the consideration that the variation of a spin at given site should depend on the other components of that spin itself. And that gives us a contribution proportional to this normal vector that has been defined above. And we get eventually the OTOC definition which was there. The AXT and B00 will correspond to the SXT and epsilon times n dot S naught. So just note the epsilon square proportionality in the DXT, which we'll be looking at later as well. So what was the numerics that we implemented? We took Runge-Kutta 4 iterator. The spin chain basically means that a periodic boundary condition was used. Number of lattice sites was 2048. Initial perturbation strength was so. And after sufficient averaging, we obtained the decorrelator maps for the two cases. Left one was the previous result that showed basically a ballistic spreading of the decorrelator, symmetric from the original site of the perturbation. And we observed such a symmetrical spreading in our non-reciprocal interaction case as well. Definitely, there's some difference in the slope as well, and that is the point of explanation as well later. So qualitatively, both the decorrelators are quite similar. The spreading from the initial site of perturbation is left-right symmetric. However, that needn't be the case always. When the contribution from both the precession terms is taken into consideration, basically lambda and mu coefficients are non-zero, then we see that this symmetry from the site of initial perturbation is lost. And this is one of the examples that we have chosen specific values for the lambda and mu coefficients that gives us a decorrelator spreading that is not left-right symmetric. Now, the quantification of the chaos, this empirical formula is used to define the decorrelator in an envelope right at the edge where the decorrelator separates from region of 1 and 0. So with this, we can find out the Lyapunov exponent and the butterfly velocity for the two cases. So we just plot the log dxt by epsilon square against x by t, and we obtain the butterfly velocities for the two cases, 1.64 and 1.32, and the corresponding Lyapunov exponents as well. Right. So now to explain this left-right symmetry in the decorrelator, we did partial analytical calculation where we took the generalized case of the dynamics and we inverted it under a spatial inversion operator, and we see that the equation doesn't stay invariant. However, we assert that there must be a second operator that restores this invariance under special conditions, and we tested the specific solutions, the particular solutions of that operation, and we found that this happens only for the case of lambda equals 1 mu 0, which basically corresponds to the Hamiltonian dynamics case, and the other case is the driven dynamics case. If lambda and mu both contribute non-zero in non-zero fashion, then that gives us the equation 9, which is basically not going to stay invariant. So now just to take this analogy a couple of steps further, the transformation that gives us this invariance in the equation gives us a spin at site minus x correspond to spin x, a 1-1 mapping between those two spins such that after the transformation O and X at time t, it gives us plus minus S of minus xt, and then we map it to the definition of the decorrelator. So we are able to get this equation SA dot SB, where B is the perturbed copy and similarly D is the perturbed copy of C. And since the perturbed copy just differs from the original chosen copy by plus minus strength of the epsilon perturbation, eventually when plugging into the decorrelator definition, it both are similar up to an order of epsilon square. So this basically explains the left-right symmetry in the decorrelator graphs that we saw earlier. Now, finally, I'll talk about the non-equilibriumness of the equation that we chose. So again, we can choose the completely generalized dynamics that we saw earlier. And we see that when we take the power dissipation, again, there's a slight trick here. We are using the Hamiltonian, which is corresponding to the nearest neighbor reciprocal interactions. But even when we choose this dynamics and then apply that, we see that only the mu term contributes to the power dissipation factor, and then by taking a continuum limit, we find the h dot term equal to, proportional to mu and the other constants which are there, and the third term, the spin product, the scalar triple product which is there, that is the term that we will eventually integrate and do a power counting, which I'll show next. So what we do is that to do the power counting and the take into account the contribution of that term, we write down the coarse grain 1D Langevin dynamics corresponding to that, where we are only adding the precession contribution from the active term, actually the driving term, and other term is just the diffusion term. We ignore the lambda term because we know that it doesn't contribute to the power dissipation. And then we write down the dynamic actions in terms of the MSR response fields. So A naught is the unperturbed field, and then A mu is the term that contributes to the power dissipation factor. We take the average of this term and take a first order perturbative calculation at the mu vertex, and that gives us, after going to the Fourier space and counting the contributions from all the term, that gives us a 6-point correlator, which has the following contributions. And after breaking down those distinct contributions, we get the final integral of this form. And this form, after doing a power counting, we see that this is convergent in both the ultraviolet and the infrared limits, which basically says that we get a finite non-zero power dissipation for the driven dynamics case, which is not going to come for the just the purely precessional dynamics term. And this driven dynamics can be related to a non-zero entropy production as well. So eventually, so finally, I'll just summarize what we saw. We saw the ballistic spreading of decorrelator in the 1D Heisenberg chain for a non-reciprocal and non-Hamiltonian dynamics. The spreading we saw was left-right symmetric for a purely antisymmetric exchange. And we presented a partial analytic understanding of that symmetry. And we finally characterized non-equilibriumness of the dynamics through a rate of energy dissipation. My acknowledgement for funding is for the Union Grants Commission of India. Thank you.
Questions?
Oh, it's university. Sorry. Okay. Yeah, I may have overlooked that. Sorry.
Yeah, so one question was, so when you wrote energy dissipation, is it always negative definite or it can be of either sign?
This sign? Oh, so, okay, so this basically depends on what H, the minus sign is just from the interaction that we earlier looked
at. So
at.
I'm saying H dot, like 15, equation 15.
Right.
it can be of either sign, or it's
No, no, it is always negative because the initial interaction that we consider H is equal to minus Sx plus 1 dot Sx, right? So that is counted over all the lattice sites. And then when we take this equation and take into account all the contributions, so that does leave us with a negative sign only. And that is essential.
Sx dot, that term could in principle be positive or negative, right?
The cross product term, you're saying?
The dot product term?
Oh, the overall dot product
Yeah,
term. Yeah, it can be. So del square,
and this is sum over x, right?
yeah, this is summed over x.
So is that, I mean, it could have either sign, right?
Or right, it could have. I think the point
So I'm
would.
asking, like, if you have a finite system, does it go to a fixed point, or can it go to a strange attractor or something? This dynamics.
Oh, this specific. I think we look of. I don't think we have looked into the attractor part of it. We are just seeing that dxt is there, which is corresponding to the spreading of chaos. So I'm not sure if we can study about that. So just pertaining to this equation, that's the question,
I mean,
right?
is it completely dissipative, or actually it can be both positive and negative, so it can go to some non-trivial state?
I mean, our general point was to mention that this is dissipative. What you mentioned is correct, that this triple product can be positive as well as negative depending on this contribution. I think the argument for that would be that this plus and minus sign that we take in the initial equation, this summation over all the sides eventually does give us positive sign. I forgot the thing, but it is eventually positive only. The contribution has to be positive.
Like numerically, you are saying you have.
Yes, this contribution is always positive. Yes. So it doesn't go into the other.
But it's not obvious.
Okay. Yeah, I guess so.
Okay.
Yeah.
Other questions? So you wrote a Lajba equation.
This one.
After that.
Yeah.
So there, I think it looks like the dissipation. In this equation, the dissipation is always positive. Yeah, and also noise term. So it gains as well as dissipates. It loses and also gains. So
Yes.
Did you try to derive it?
So what we did was to write down the integral and the contributions for this. We took the contributions from the Green's function that comes from the dissipative terms itself. And since we saw that the lambda term doesn't contribute to the energy dissipation, we dropped that term. And whatever Green's function we wrote to write down this correlator, we use that Green's function corresponding to the diffusive term only. So that is corresponding just the dissipative part of it.
Okay. Any other question? Okay, if not, let's thank Nisarg once again.